Alright, so we're identifying, so we're in lesson 9 right now, and the objectives for lesson 9 are differentiate between cis and trans isomers, identify asymmetric centers, and then drawing and naming enantiomers. Okay? So the first thing we want to do is differentiate between cis and trans isomers, and the way we're going to do that, I'm going to show you with a model first. A cis and trans isomer. Cis and trans means opposite or on the same sides, right? So let's look at this. Now this is an sp3 hybridized. You can see it's trigonoplanar. Can you see that? So these are sp2 hybridized carbons. And if they are, can you see that must be a pi bond? Okay, two sp2 hybridized carbons right next to each other. Sorry, sigma and a pi bond. Right, but I'm only showing one of them, but alright. So if that's the case, there's restricted rotation about this bond. And if there's restricted rotation, this thing does not freely go from that to that. Right? Because it's a double bond. Okay? And I've only got one stick in there to show you. But you can tell because it's trigonoplanar. That said, if it's got restricted rotation, then that is different than this. Okay? And one of these is cis and one of them is trans. And when we're saying cis and trans, we're always talking about cis and trans with respect to two particular groups. So this is trans with respect to pink, and this is cis with respect to pink. Can you see that? Okay. Trans is across and cis is on the same side. Now let me point something out here. It's an occasional mistake. Which is this, cis or trans? Which is that, cis or trans? And the answer is it's neither, right? Because these are, I guess you'd have to say these are trans, they're on opposite sides, but when we're talking about cis or trans, we're always talking about things on separate carbons. Okay, so if they're on the same carbon, of course they're on the opposite sides, right? So we never use cis or trans with respect to this particle right here, this molecule right here. Because look, you can see that if we could break this double bond, twist it, and reform it, it would be the same thing. So this does not exhibit cis-trans isomerism. These two do. If I could take this double bond and break it and reform it, it'd be something different than it was in the beginning, right? So, alright, these two, this exhibits cis-trans isomerism. These are trans with respect to each other. These are cis with respect to each other, and these are neither. Okay? And cis-trans isomerism also shows up in the context of ring structures. So, can you see, look past the green for a second and see if you can see a chair conformation of a cyclohexane. Can you see that? Okay. So these two are on, say, the 1,2 carbons. 1 carbon, 2 carbon, 3, 4. Okay? So this is a 1,2, right? And can you see, are those cis or trans with respect to each other? Those are trans. And can you see that if we go through a ring flip, right? Let's do a ring flip here. Okay, they're still trans. Okay, because here's where the other thing is coming out, the other hydrogen, right? My two thumbs are where the hydrogens would be coming out, right? And so they're definitely still trans. Be careful now. That looks like they're on the same side because they're both equatorial. That's the other point I would like to make. That if they're cis and trans, if they're 1,2 and they're trans, they're both going to be equatorial, or both axial. Do you see that? Okay. What about 1,3? 1, 2, 3. Can you see that? These are also trans with respect to each other. Okay. But if one is axial, the other one's going to be equatorial. Okay. So these two are trans with respect to each other. I know that because I see this other hole right here, okay? So this is on the same side of the ring. This is on the underside of the ring, or the average plane of the ring is how we've been calling it. This is on the underside of the average plane of the ring, right? So these two greens are trans with respect to each other. And if it's 1,3, then they're going to be axial and equatorial, or equatorial and axial. Watch this. We'll do a ring flip, and we'll see. Right? That one was axial. It went to equatorial. This was equatorial. It went to axial. Okay, so play around with that a little bit and prove to yourself what the pattern's going to be. If we put that in paragraph form, it'd be really complicated. These are all trans. This is trans with respect to that. Of course, I mean, I guess you can see that these two are cis with respect to each other, right? Okay. But in this one, I use a different color to show. These are all cis with respect to each other. They're all in the average. See, if we take the average plane of the ring, sort of bend that down, you can see that they're all on the top side, right? Okay, let's make this into a chair conformation. Can you see that? Chair conformation? Okay. So these are cis with respect to each other. And if they're 1, 2 in cis, then one's going to be equatorial and axial, or the other way around. And 1, 3, if they're cis, they'll both be axial or both be equatorial. Okay, so that's cis-trans isomerism. That's the first objective for lesson 9. We did cis-trans isomerism both with double bonds and also with ring systems. And the point is restricted rotation, right? We don't have a free rotation about these sigma bonds because they're stuck sort of stuck by the ring, right? These are restricted by the pi system. I don't show the double bond here, but there's a double bond right there. And therefore they do not have free rotation. They jiggle a little bit, but they're mostly planar. That's what we call them, planar. Okay? The second objective is to identify asymmetric centers in molecules. And what we're going to do is we're going to simply say, this is super simple. Now I didn't say easy, but super simple. An asymmetric center in a molecule has to have 4 distinct electron groups coming off of it, or else it's not an asymmetric center. Okay? It has to have 4 distinct things coming off of it. Alright, and that's it. So this has got 4 distinct things coming off of it, and that's got 4 distinct things coming off of it. Actually, I said asymmetric center here. More precisely, these are stereogenic centers. I'm not going to differentiate between asymmetric centers and stereogenic centers very carefully in class, but Bruce does a good job of that in section, I think, 4.3 or 4.4. Okay, so 4 separate and distinct things coming off of it, or electron groups coming off of it, that makes it a stereogenic center. Okay, and then finally, drawing and naming enantiomers, and this is the big one for lesson 9. And drawing and naming enantiomers, what we're going to do is we're going to first of all say that a wedge is in the plane, or rather, a wedge is coming out toward us. Straight lines are in the plane of the paper, and a hash is going back behind the paper. And what we're going to do is we're going to say A, B, C, and D. I sort of just arbitrarily put these down. And what you need to do when you're naming this is, number 1, orient molecule such that the smallest group is going back behind the plane of the paper. Okay, the way I'm going to do that, I just arbitrarily chose this A, B, C, D, by the way. Let's say that A is the smallest and D is the biggest. A, 1, 2, 3, 4, those are the sizes. Or if D is the biggest, we'll say D is the highest priority. It's going to be 1. C is the second priority, 2. B is third. Okay? So what we're going to do is we're going to rotate this thing so it goes back behind the plane of the paper. The way I'm going to do it is I'm going to do 2 switches. If any one switch is going to give us a mirror image, but if we do 2 switches, we'll be back to the original. So I'm going to say C is up there, A is here, D is here, and B is here. Do you see how I switch these A and C? Okay, that's one switch. I'm going to do another switch. But I want A to be in the back of the paper, so let's keep that there, and let's switch those 2. I want A to be in the back. Now if A is in the back, I'm sorry, number 1 is assign priorities. Okay, number 2 is orient the molecule such that the lowest priority is in the back, which I've done here. And number 3, draw an arc from highest to lowest. Okay, 1, this is 1, 2, and 3. Okay, counterclockwise is S. Clockwise is R. Okay, so since I went counterclockwise, this is S. All right. So that's how we assign the orientation of this enantiomer, and let's name one now. Let's go with carbon, iodine, hydrogen, bromine, and chlorine. Okay, so assign priorities. We can do this pretty easily. We can see iodine's the biggest. 1, 2, 3, and 4. If there's a hydrogen on it, it's always going to be the smallest, right? That's the smallest molecule. That's the smallest atomic number. All right, so let's first of all put the hydrogen in the back. I'm switching with bromine, you can see. I've got to do 2 switches to make it the same absolute configuration. So hydrogen still needs to be in the back. Let's put bromine over here and chlorine over here and iodine. So iodine's priority 1, 2, and 3. Then we draw our arc. 1, 2, 3. It's counterclockwise again, so this is S. So the way we name this is methane, is the root structure, right? And it's got an iodo, it's got a bromo, it's got a chloro, and these go in alphabetical order, so it's bromo, chloro, iodo, methane, and we put an S in front of it. It's S, bromo, chloro, iodo, methane. Alright, there's a simple example, and we'll do some more elaborate examples in class.